It is 10:30 Eastern Time, and we are ready to start our very first reverse pitch of the day. This first reverse pitch is going to be moderated by Lang Men from Stanford. It's going to be all about resiliency and outage optimization. All right, Lang, over to you.
Thank you, Hannah. Good morning, everyone, and good afternoon for the folks in European countries. My name is Liang Ming. I'm the Managing Director for Stanford Bits and Watts Initiative. I'm very delighted and honored to moderate and chair today's session. Join me, we have 4 distinguished women in power and women in data science are going to present this topic, which is AI for grid resilience and outage optimization. And we put this panel from 3 different types of utilities perspective. We have a public utility, which is from Nicole Lakoff from Lower Colorado River Authority. And we have electrical co-op, Emma Stewart from NERC. We have invest-owned utility, have Anna Maria Nango and Miriam Variani from Pacific Gas Electric. So agenda of today is each of them will have 50 minutes to present their perspective. Then we're going to take some questions in the end. We'd like to welcome all the audience to join us for this conversation. So if you have questions, please go to the bottom of your screen. You will see a Slido and type your name and email. You're able to submit the question and join the conversation with us. I also like to remind everyone that we'll also have another breakout session for this conversation at 3 p.m. Eastern Time. We'd like to have you to join us. Without further ado, I'd like to hand it to our first speaker, Nicole Lakoff. She is Transmission Operation Engineer at Lower Colorado Riverside Authority. Nicole, the floor is yours.
Thank you so much, Liang. And good morning, everybody. I hope everybody is enjoying this event. I have to say that working with EPRI on just arranging this call has been really interesting. I can't help but feel like we're in the future of conferences. These virtual events have a lot going on in the background, in the backstage. So thanks so much. Like Liang said, my name is Nicole. I am an engineer at Lower Colorado River Authority, or LCRA, in Austin, Texas. And I am an engineer supporting transmission operations. And for my reverse pitch, I am talking about using artificial intelligence and machine learning for economic outage plan optimization. To give just a little bit of background around what my team does in operations is around outage planning. So a core mission to my team is to produce an outage plan that is N-1 secure for our organization. And what that means is we receive outage requests from various internal and external stakeholders. So these are outages to support capital projects for both LCRA and our customers, and also maintenance requests to ensure that we are keeping our grid in tip-top condition. And we take each of these requests and we study every single one to confirm that they are N-1 secure. The way that we do that is by performing an analysis called contingency analysis, which is just a regular power flow where we apply the outages that we're studying and the outages that we're already planning to take, and we apply each single contingency. A single contingency could be a single line or a transformer or losing 2 lines that share the same structure. And we ensure that there are no post-contingency violations, like overloading a parallel path or low voltage or high voltage. And as we're studying these requests, we attempt to mitigate violations through mitigating actions. And that can be rerouting power by opening a switch somewhere else in the system, or it could mean turning on a cap or changing taps on a transformer. And sometimes when there's flexibility for these outages, we can even work with the requester to resequence outages so that we avoid conflicts that are causing violations. So there's a lot of moving parts, a lot of back and forth, but ultimately what we try to do is produce an outage plan that has no negative impact on reliability. However, sometimes despite our best efforts, we have to put outages together that have an impact on reliability. And the only way that we can mitigate those reliability impacts is through generation redispatch. So that's not just opening a switch or turning on a cap. That's actually taking a generator and changing what the output of that generation is. To describe what that looks like, I've got a very simple example that I took from a training from ERCOT, and it's available to anybody if you're interested in learning about how the ERCOT wholesale market works. You can go to their website. But in this example, we have one load zone. We have 3 generators labeled as resource nodes. And we have some transmission lines, and we have a 345 kV hub, which is probably like a substation or a switchyard or something like that. So in a perfect economic dispatch system that is totally non-constrained, so there are no outages applied to the system, and there are no inherent system weaknesses just based on like small lines or derating or anything like that. The way that load is satisfied in these systems is in ascending order of the cost for generators to produce electricity. So in this example, I clicked on the wrong place. I got to click over here to advance the slide. So in this example, we have 1,100 megawatts at the load. And since this is a non-constrained system, that means that the least expensive generation is going to satisfy the load first. So the first 200 megawatts is going to be satisfied by resource node 2. The next 350 megawatts is going to be satisfied by the second least expensive, resource node 1. And then the last 550 megawatts is going to come from the most expensive generator, which is at resource node 3. And since this is a fully most economic dispatch, the price that everybody pays is the same price that everybody receives for producing this electricity. We determined that price, based on the cost that it took to produce that very last megawatt. Since that last megawatt came from resource node 3, that's the one that sets the price for everybody. So this is the example of what we like to see. But what happens when we add constraints on the system, such as by taking outages on lines? This picture looks different now. There are 2 constraints now. There's 100 megawatts constrained between resource node 2 and the 345 kV hub, and there's a 400 megawatt constraint between the 345 kV hub and the load zone. What this means is that resource node 2 can no longer be producing 200 megawatts. It has to be reduced to produce only 100 megawatts to satisfy that constraint of 100 megawatt limit. Resource node 1 likewise can't produce 350 because of that 400 megawatt limit between the 345 kV hub and the load zone. So instead, it's reducing its output to 300 megawatts to satisfy that constraint, leaving the other 700 megawatts to be produced by resource node 3, the most expensive option. So the way that the market changes its signals is it's changing the price that is offered to the generators so that it doesn't incentivize the generators to produce more than what the constraints will allow for the system. And there are ultimately a lot of differences between the numbers on this less economic dispatch scenario and the most economic dispatch scenario. As outage planners, we are trying to minimize that delta. We want to have the least amount of impact on the market. And if we can change our outage plan to minimize that, that is what we try to plan to do. So you can certainly deterministically calculate what the market impact of an outage is going to be. You need something like what we're looking at right now. You need economic models, so you need those energy offers from all of those generators. You need the electrical model. You need the outages so that you can calculate your constraints, and you need load zones. For outage planners like us who are already performing a contingency analysis, it can be computationally expensive and require more models to calculate this cost. So my reverse pitch is that we leverage artificial intelligence and machine learning to create cost models for outage planners that don't have these economic models available. Like I mentioned, there are deterministic models that you could use to create training data sets. In ERCOT, the network power model U-plan is available. Additionally, you could probably make one. I think EPRI is doing work in Program 39 that they may already have like an economically informed power model. In addition, there's lots of historical data on the ERCOT market information system that could be mined for creating and training these cost models. And I have listed just some examples of data that is available there. So in my mind, not necessarily being a data scientist, but just an electrical engineer, I could see two methods of creating and training a cost model. You take your important system inputs like transmission outages, generator economic information, and forecasts on load and renewable generation. And you can either create your training data sets deterministically by using U-plan, and then using the outputs from that model to train your cost model, where the output of that model is some sort of transmission outage cost, whether it's dollars or whether it's low, medium, high, or whether it's like a percentage, some sort of indicator that outage planners can use in order to compare different outage scenarios and minimize the market impact. If you didn't want or you didn't have access to a U-plan, but you had access to historical data, you could take those same system inputs and perhaps train a cost model that would give you something like a similar transmission outage cost. So this cost model would be super helpful for existing automations that many create for outage sequencing. So Project 39 in EPRI is working on a product like this. My team also has outage planning automation products where we take outages and we apply them to our models and we identify violations. A cost model trained through AI and machine learning could be well housed in that whole process, where we can ultimately use the cost of an outage as a parameter for making decisions about it. The opportunities for collaboration just within EPRI, I think there are a lot. Program 3914 already is doing so much in operational analysis and outage planning automation. There are certainly members like LCRA that are interested and can partner with artificial intelligence and machine learning developers to test and to train models. And I suspect that there's already opportunity to consume these types of cost models. So I think that is the end of my presentation. I hope that it's offered another perspective.
Thank you, Nicole, from LCRA, and share with us transmission operation perspective, how we can use the AI to better manage outage. The next one to the stage will be Dr. Emma Stewart, Chief Scientist from NERC. Emma, the floor is yours.
Thank you, Liang. Hi, thank you for inviting me to be here today. I think I'm starting to move forward the slide. I apologize. Something really interesting from all of the presentations that I think we're seeing just now is that despite all the differences in utility structure, we all have interestingly similar problems going on. I actually joined NRECA approximately 110 days ago at this point. I have a background in power systems engineering, but my research and leadership roles have stemmed into artificial intelligence and machine learning, along with various things to do with cyber and resilience as well. So it's been an interesting journey to get here. NRECA Research, apologies, I'm trying to move forward again. There we go. I did want to structure here a little bit of what NRECA and NRECA Research do and the size of what we work on. We perform R&D on behalf of 900 cooperatives, essentially, providing useful results, engaging with state, federal funding. To understand what the cooperatives are, they have G&T, which is generation transmission. There's also 832, and I'm learning all these numbers myself at the moment, distribution cooperatives. In general, we serve around 42 million people with these members that are part of the NRECA research world. Can you move the slide forward for me? Sorry, it seems to be delayed. Okay, thank you. So I wanted to cover here what the cooperative service areas actually look like and how much landmass they cover. As I said, there's generation transmission and also distribution. This was just mapping out where the generation and transmission co-ops actually live and the structure they are in across the country. As you can see, the landmass is pretty huge, and they also, in the distribution area, they cover primarily the middle of the country, but there's spread from, I think, 48 different states at the moment. So just level setting the type of things we work on and the scale of data that we've been considering in these problems. So next slide. Thank you. The NRECA research mission is slightly different. This is the area I primarily lead at NRECA now as the new chief scientist. The idea here is that we do research both on behalf of and with federal funding, useful research for development and demonstration and providing value to the co-ops. It spreads across all realms of electric energy delivery systems, and also actually delves into gas, water, and all the other pieces that are definitely interconnected, as has been very obvious in the last few months. Energy sector, cybersecurity, data analytics, sensor and control networks, and equity and energy access are the four main focuses. We do work with all sorts of different people, including universities, national labs. All of the above approach is the role here. So next slide. So getting down into the technical and what we actually wanted to talk about today, what problems and challenges we've seen in the AI space are interesting when it comes to outage and resilience management. Incipient failures of components, and vegetation management are something that's inherently interlinked, but all require different types of data to be analyzed. I think prior Nicole talked about the economic space. Well, in the physical space, there's a similar problem of different scales and types of data that we want to combine together into being able to predict and prevent catastrophic failures of components, which can lead to also vegetation problems. Incipient failure is one of the really interesting challenges. We do want to be able to use equipment for as long as possible, extend its lifetime. But as failures develop within pieces of technology, the ability to detect that even a small thing is starting to go wrong that could have an easy repair strategy before it actually ends up giving off a big smoke signal would be very helpful to do. But that requires imagery, signatures, other types of things going on. I think artificial intelligence is one of the ways we'll deal with some of that. There's many causes and effects that can go into this. Timescales to do with signature recognition locally, distributed analytics, being able to work between points to combine data sets. Data fusion is a challenge as well. And being able to actually work out how severe a problem is. If you want to send out a field crew, knowing that they're going to the most important location at the right time is critical, and it's not often understood how to use data in that realm. We do have other work on how to predict, diagnose, and prescribe centrally. Also, being able to take a holistic view of the whole system is a challenge. And then also being able to come up with new remediation strategies that aren't just generally the traditional switching and replace. We can look at how to use, for example, distributed resources, use microgrids, or use other types of technology in the field as well to help respond there. Sensing on all components is prohibitively expensive, not just because of the sensing, but actually because of communications. Working with the rural entities, things can be remote. They can be at places at the end of a very long line, and you don't necessarily always want to have someone have to go out and collect data. So how do we put all those things together into this picture that can be used quickly and easily by the co-ops and by their field crews also? Another interesting piece is the size and the amount of data we have from each co-op. Some of them are 3-feeder mom and pop shops that are doing a great job of managing their system, but they don't have enough data to actually use this or even necessarily the business case. We want to make sure things can be done there in a smaller way, as well as scaling up to the larger G&T environment also. Next slide. Something also that I think is really interesting, I joined NREC and found out we have a huge UAV, unmanned aerial vehicle program that does a lot of the scanning of the lines and does a lot of the essentially drones doing pictures of the system. Super useful in the rural environment because you don't actually always want people to go out driving in the snow to see a picture of what's going on. It's really useful for outage management assessment, again, prioritizing restoration. Also disaster response, I think, has a huge application here. It's not a surprise that when there's a large-scale weather event, you see the mutual assistance teams going out, coming from one co-op to the other to help. I think that the combination of images in this kind of world would be really helpful. The picture on the right is some of the work we've been doing, very simply looking at pole tilt, which sounds simple, but the image recognition and combination piece is a challenge. I think there is a lot of interesting work that's been coming from the medical field and how to interpret things like MRIs, and also from the defense field and how to use these kinds of approaches. But translating that over to the grid world has been something that's taking a little bit more time. So really understanding those approaches. Predictive restoration here is also really interesting. So next slide. So one of the challenges here we also talked about was how to actually prioritize humans, which I think is a really interesting approach as well. I mentioned mutual assistance. When there is a large outage, we see field crew trucks coming from afar to go and help, basically to work out how to fix something. Optimizing that, I think, is an actual data analytics challenge, making sure we're sending the right people to the right place from the places that didn't need help in the first place or aren't about to have a growing failure themselves. I know that generally right now is actually a human analysis problem. People schedule and determine where people are going, but I think combining that with significant AI and machine learning techniques would be a really good way to start introducing this as well. One of the projects I wanted to mention was how do we do better, essentially? How do we manage outages in a way that optimizes the use of new technologies? And here we were looking at how to essentially have recloser and restoration tools placed in a way that's optimized for maximum bang for our buck, essentially. Not every co-op has a huge amount of backup funds to install as many reclosers as they might want. So how do we optimize that to get the maximum amount of information from them, but also add things like advanced sensing streams and validate what is going on and make sure we are able to cut those outage costs in time quickly. So that all leads into, I think, my last slide, which was talking about a large event, which has already, I think, actually been mentioned. But if one of the things I think that's ripe for collaboration is looking at those big challenges that happen when it's uniquely spread across the bulk system, generation, transmission, down to the distribution, down to the customers. These events aren't driven by any one source. There's not necessarily one problem that we can solve and this will never happen again. When things are driven by extreme weather events like cold weather and other physical factors, there's a significant mix of local physical system level events, along with emergency services and other pieces coming into play. There's a mixed priorities. Everyone wants help immediately. Everyone wants to be restored immediately. Being able to do that restoration is inherently dependent on what technologies you have out in the field, and also data integration that's well above the cognitive capabilities of a human at this point. I don't know any person in research, and I know a lot of them from the national labs, that can look at transmission, distribution, and humans together and come up with a solution that's necessarily correct. So the scale of data that happens during these problems is enormous, but also in some cases limited, which I think is the chicken and egg problem here. We have these events that happen. We do have a plan afterwards of how to repair things, but we don't necessarily have plans of where we should be putting data sources in future to get the most out of these AI applications as well. So there's all sorts of tools that could go into this from all levels that I've seen, to with load assessments and disaggregation, advanced restoration tools, looking at how humans are dispatched, how we coordinate the system. Things like cold load pickup are not necessarily solved when there's a large scale outage and you're trying to restore, and as it happens, everyone had their heaters on at the same time. So that generally will pop a fuse, and then you're back into the human going out in the snow to go and replace the fuse. So being able to do a post-mortem assessment all across the levels with data involved and make better decisions, I think, is one of these areas that's ripe for collaboration, both with the AI communities and with the different scales and different types of utilities that were involved in these systems. So that is my little introduction for today. So thank you. I appreciate the time to talk.
Terrific. Thank you, Emma, and for sharing with us co-op's perspective. Co-ops is very important, as they literally have a very limited resources, and how we can get them ready for the advanced AI application will be very interesting. The next, we'll have a tech team presentation from Pacific Gas Electric. Joining me will have Anna Maria Ningo, is a technical project manager of the strategy data science team, and also Miriam Variani, and data scientist at Pacific Gas Electric. Anna Maria and Miriam, floor is yours.
Thank you. Good morning, everyone, and thank you for having us here today. It's really great to be able to share some of the interesting work that we've been doing. So again, my name is Anna Maria, and I am a technical project manager with the strategic data science team. I also have a background in transmission planning, substation engineering, and asset management in general in the electric utility. So yeah, today we're gonna talk about a specific project called EPIC 320, which seeks to implement data analytics for predictive maintenance. And we are focused on a very specific problem, which is that many asset types usually run into problem, or the utilities run them to problem or to failure. There is sort of a lack of predictive maintenance for certain types of assets, and that leaves the utilities usually open to reliability, safety, and other types of risks. So the proposal here was that we use existing PG&E data sources such as AMI and others. Then we are able to develop machine learning or predictive failure models, and based on that, we can identify the conditions of indicative failure, incipient failure, and equipment. We have different phases planned out for this project, and the first one that we're working currently on is the first and the second one. We're working on distribution service transformers. So essentially, what we're trying to create, to put it in an analogy, is kind of like a car's check light engine, where if you see it, you can take action before it actually, something really bad happens to your car. You can kind of take it to the repair shop, right? So that's the goal here: maximize the lifetime of the assets, as well as being able to detect any anomalies before they actually take place and cause outages or wildfires or other things like that. So it's important to keep in mind that there are different time horizons in which maintenance in general can be looked at. So for our project, our focus is days to weeks. So we're looking at trying to predict equipment failures that will take place from days to weeks. And there are other parts of the company actually looking at the other time horizons, but this is just for the scope of our project. So as you were imagining, there are many different benefits that can come from implementing this type of project. There are benefits in reliability, there are benefits increasing public safety and customer satisfaction, and there's also benefits projected on the cost savings. There's a lot of different outages and metrics in general that can be improved by implementing this type of approach. So with this, I'm gonna transition it to my colleague Miriam.
Oops. Hi, everyone. So yeah, I'm also a data scientist in a strategic data science team. My background is in electrical engineering and like applying data analytics to energy problems. So I will start with a diagram of assets and terms that I will be using in the next slide. So we are predicting failures for service transformers that is shown in the middle of the diagram. And on the high voltage side, the transformer is connected to the primary conductor on a feeder. And on the low voltage side, the transformer is connected to secondary conductor and customers. And the customers, they have smart meters through we have readings through service points, and the data could be in 15 minutes or hourly intervals. And and overall we have about 600,000 transformers in a scope for this project. Next slide. Okay. So what we are predicting is that we are predicting transformer failures with 30 days into the future. So if you consider the horizontal line in the middle as a time, and the red area is where failure is incipient, and we have like voltage anomaly, we can read like that we can see from the smart meter readings. And the orange area is where PG&E is notified about the notification about the voltage anomaly, transformer failure, and until when the transformer is like replaced. So if our model predict transformer failure during the time that notification is active, we give credit to our model for a true prediction. If not, that would be a false positive. In terms of feature, the model is developed and benchmarked with voltage anomaly features so far, but we have like many other features that are in progress and will be included in the model soon. So for voltage features, we have two sets of data. One is aggregated voltage data, which is like aggregating the voltage under like each transformer, starting from phase level. And the other one is neighboring voltage features. This one is inspired by a methodology used by Comet. So in normal condition, voltage will drop from on a feeder from source to load. And but if there is a like big voltage difference between a transformer and neighboring transformers, that could be a sign of bad transformer. And the additional features that we are working on are temperature data, transformer loading time series, transformer overloading flag, and transformer equipment characteristic. For the labels, we use the asset management database failure labels for phase 1 of the project. So this includes all kind of transformer failures, or I would say anything that causes a travelman to replace transformer. This could be due to like a car accident to a pole, lightning, corrosion, or like transformer failure caused by like winding failure. So we found that we have a wide variety of failures, and we are not necessarily interested in those failures because there is no voltage anomaly for many of those failures. So we did some filtering, but on phase 2 of the project, we decided to focus on outages that can result in an ignition or customer outage. So we focused on like heat wave failures, the outage related failures, and also the ones with ignition. So I talked about the features, labels, and for model development, we followed the like best practices in implementing like a machine learning model. We started with raw data, with like define our labels, and then the features, and also the data prep, feature engineering, and the implementation, considering like the cross validation and the train and test split, and eventually the validation of the model. And for the implementation, we use random forest and gradient boost models. So I think I'll pass it back to Ana Maria.
Yeah, thank you, Miriam. I can close this out. So these are some preliminary results from phase 1. So the idea is that our model makes some predictions, identify transformers where it believes there is incipient failure, and then there is an engineering review of experts basically that can try to understand why the model is predicting that and whether they believe there is an issue or perhaps there is no issue or false positive. And then after that, there is also a process in the field where the field crews will be going onto the site and taking a look at the potential transformers identified. And then some of these transformers will ended up being replaced or repaired. That's typically how the flow goes. So we've had some success having already some equipment that we identified in our model, goes through engineering review, then goes through the field inspection, and then turns out there were issues with the transformer. So they take the corrective actions in the field. All right, and this is a quick example here of how we are using some of these features that Miriam mentioned. And we created something that's called the bellwether voltages. We can see that blue graph on the bottom. That is the transformer voltage, and at some point in March, it presented an anomaly. So our model flagged it, and the colors are a little bit inverted. So the blue one that you see on the bottom is the same as the red one that you would see on the top. And what's going on is the model flags it because it sees that it's very different from its neighbors. On the top one is comparing it to the neighbors. So it's comparing it to the purple and the other blue voltage there. So it sees that it's significantly different than its neighbors. Then some sort of corrective action in the field was taken, and then the voltage level went back to normal. And the other example that I have here, one second, or can you please move it forward? I'm not sure it's okay. Maybe it went too far. 1 second here. Okay, so this other example, it's apparent energy theft. That's another kind of interesting finding that our model has been able to catch. And the way we can see the voltage is very low. However, when we compare it, and I'm not showing it here, but when we compare it to the load, you would expect that the load would be higher, but it actually didn't seem, we didn't find any anomalies in the load. So once again, some corrective action took place. That was around where it says Tuesday 09. Then some corrective action took place, and then the voltage went back to normal compared to its neighbors. And the last part here that we want to share about our project, maybe you can help me move it forward. Okay, it's there, sorry. the last part here is our next steps, basically where we're at. So we always look at this kind of in 3 pillars. What are we doing as far as a product development, then in the model, and then the features. So for features, we're looking to add more features such as forecast and historical temperature, transformer interval load, and equipment characteristics. We believe these features will be important and kind of make the model smarter and better to predict these incipient failures. In terms of the actual model, we're looking to do some automatic failure classification, continue to do model tuning or refinement, and then as far as the product, continue to create a process so that we can have those field inspections that I mentioned earlier, and then have a feedback loop to our model from those. And also trying to figure out a path to production. Right now, the project is funded under an EPIC program, so we can't do a whole lot of products to put it into production, to create this path to production is where we kind of stop. We create the path to production, and then in terms of making it operational, then there have to be other teams in the company and other projects that actually take it forward and implement it fully. And that's all we have. Thank you very much again. Hope this has been helpful.
Great. Eric, I'd like to have both Anna Maria and Marianne stay on the stage for a minute, because when I review their slides, I do see a very interesting backup slide they have, which can help us to kick off the question and the answer. And when we talk about AI and machine learning, we need the data. Then what's the volume of the data? Typical utility like Pacific Gas Electric, very large, invest-owned utility, we're going to receive every day. What's the volume of data we're talking about? So Eric, could you pull out the slide again? I believe the first backup slide is discuss the data issue at Pacific Gas Electric. Two more slides down, please. Not backward, forward, please. Click again. One more.
One more, I think.
Another more, please. One more. Yes. Go ahead.
Yeah, so PG&E typically collects approximately 10 billion data points every single day. So yeah, we have a huge amount of data. There are some challenges though, as you're collecting all these data, making sure, it's there's good quality data and that you can actually use it for a project like ours, right? Because the data, when it's collected on the first hand, it has probably a very specific purpose to serve a specific team or, get some kind of insights. But what we're doing, we're kind of like scrapping that data that other people were collecting, and other teams and other projects in the past have needed this data for, and we're just kind of scrapping it and trying to use some of this for our own project. But that was the whole premise, to be able to use existing data sources as opposed to going out and put in sensors or trying to collect new data, but trying to use the one we have.
Good, thank you. So now I'd like to invite all of you back to the stage, and we have perspective from public utility, investment utility, and electrical co-op. And first, let's talk about challenges. What were or are the challenges of getting your organization, your member organization, ready for the AI? A data challenge, hardware challenge, software challenge, or workforce challenge? Can you share your perspective, please? I would suggest let's go from Nico to Emma, then go to Anna Maria and then Marianne.
That's a really good question. I would say that given our group's propensity to grow our own tools. Our engineers have been maybe closer to the data than maybe past experiences that I've had in other utilities. But definitely data silos can cause challenges. You might have disparate data sources in disparate formats, and you might develop among your workforce like really good competencies in SQL, but maybe less in being able to like parse data. And we typically are electrical engineers who didn't necessarily receive data analysis training. So that's one challenge, the data silos. And then also, I think just bridging the possibilities, the organizational goals, and saying this is the data that I have, and what tools can we use to bridge them together? Because we understand electricity, we're mostly electrical engineers or operators, and we know how the system works. But being able to synthesize the data tools and leverage AI and machine learning that's outside our wheelhouse, I think that's a challenge.
Emma?
Hi. I think similar issues. Workforce is one of the big ones. We don't necessarily have a dedicated data science team at every co-op, but there's a lot of interest in growing that. One of the other pieces I think is perception of the workforce, and as the how do I put this? The new generation who have been able to work with iPhones their whole life and have a perception that machine learning and artificial intelligence actually is helpful to them. I think there's a lot of opportunities for that workforce to grow, but right now it will be potentially a limiter on how things actually be integrated from the perception view also. I think there's the data issue is probably one of the larger ones we have, in that a few years ago we did a lot of work on distribution synchrophasers. Having the use case for those was always the problem of, okay, great, we have lots of data now. Here's some use cases. How do we get them together? And not thinking that one data source can solve every single problem we have. And there's always the new shiny sensor that comes up, but not always the multimodal type analytics that go with that to leverage everything in the right way. So between data and people, the machine learning, artificial intelligence is moving forward, but data and people will probably be the biggest limiters on us for that. So.
Miriam, would you want to first this one?
Yeah, sure. So Nicole already mentioned the data silos. We also had this challenge, and when we started the project, like finding data, we had to reach out to different teams just to find the data that we were looking for. So that was very challenging, but luckily PG&E has changed the structure of the databases, and we are in a better position now. Also, I would say the labeling, that was another issue specifically for our project. The way the Travelman logged the issues for assets, that was not consistent. We had to go to the parsing the text and the issues that they entered. That was another issue. And overall, data quality, that was a very big challenge for our project, missing data, inconsistent records. That makes it very challenging.
Good. Another question coming from the audience, a little bit high level. I'd like to start some high level questions. And how do you prioritize the use case of applying AI for your company? Because you have a transmission problem, and the transmission also have operation problem, planning problem, but different application, your different use case require different machine learning algorithm, and very often also require different infrastructure to support the algorithm. And how do you prioritize your investment How do you prioritize the use case of AI application? I will open the floor. Who would like to start first?
I can jump in with one answer. That one of the ways we prioritize them is we actually sit with our member advisory groups and ask them what their biggest problem is that data and artificial intelligence could solve. That's the easiest way we actually do it. Is we take a selection of people from across the country and ask them what their priorities are and how we can help, essentially. So talking to people is actually the first answer I have. I'll hand over to anyone else. So
yeah, I would say that for PG&E, it's something similar where we get together with different lines of businesses and try to understand their issues and assess business value, but also look into, oftentimes, I won't say it happens for every project, but oftentimes there is ability also to compare the technical effort. So if it's high business value, low technical effort, I think those are the projects that tend to kind of come up first. I mean, and not to say that any of these projects are low technical effort, really, that they're all significant amount of efforts, teams of multiple members and across multiple years, but still some problems seem to be more addressable from a technical perspective than others. Some are very, very great ideas, but maybe very, very low technical feasibility. So we try to kind of balance those two.
Nicole, anything you want to add here?
Sure. And not being a like a data scientist or on LCRA's team for data, just having experience trying to solve problems with data, I think that one concept that utilities need to address when there's a problem and you want to use data to solve it is whether AI and machine learning is the right solution. Or is there a deterministic solution that solves the problem faster? Sometimes our problems are really simple and we just need a calculation applied over a lot of data sets and the technical challenge is making sure that the data is connected and you have the right data to do the calculation. But AI and machine learning can be elevated. It's not just a calculation. It's finding those relationships that weren't immediately obvious through a calculation that we can pull out of an engineering book.
Terrific. I think, both Emma and Nicole mentioned the workforce issue or workforce challenge. And I'd like to press this question a little bit more. Because at Stanford, it's a slightly different story. We have 90% of engineering school students, they have taken the machine learning or AI 101 class at Stanford. Whatever they are, mechanical engineer, electrical engineer, of course, computer scientist, civil engineer, or the ERE student, engineering resource student. And so my question is, first is, for EE student or electrical engineer, how we can help as a university, how we can help, or maybe EPRI, like professional think tank or research organization for utility, how we can help them get ready for the AI application in the future. Then on the flip side is, if I'm a student are going to graduate very soon, I have trained in AI, but I can work in Silicon Valley and make a lot of money, or I can go to utility and keep the lights on, which is very important. And how we can attract these students. They have some very basic or maybe advanced AI training, but how we attract them into the power engineering society. You can answer either one side, is fine.
It's a really good question.
The greatest answer, because I love working in power, so it's easy for me to say why I like power. So, but experience of what utilities do and what they're managing, and looking at the things that are exciting might be a good, like even rotating students through different utilities so they could see where it might apply, and understanding different options for it for their work, or where they might grow it, and eventually, yeah, they can move on to the very, very high-paying Silicon Valley job. But getting some experience on the challenges they might face might also be a good way to see or catch the students who are interested in the power side as well, or at least have more interest in where their energy comes from as well.
I would say
Nicole, sorry.
Oh, sorry. We all have thoughts on this topic.
Yeah.
I was just going to say that I think that your question is like very relevant to many, many industries, which is we rely more and more on machine learning, computer science, programming for most industries to do business better. And as electrical engineers, we kind of get lumped into like programmy folk without necessarily having the computer science background to know how to do things like correctly. So I'm on definitely the generation that was before machine learning was like machine learning 101. And I wish that I had that background, and I wish that I knew more about computer science, because sometimes I just describe myself as an engineer who has way too many SQL permissions for their own good and know enough to be dangerous. But I really wish that I had like more training. So I think that industries can help technical people who don't have the computer science background by providing more training and more awareness around that. And I think that all industries are going to be in the same boat for trying to attract computer science, technically able people in all of their technical competences. So that's not an answer,
Good.
but it's a good question.
I was going to add that. Oh, just really quick for me. I think also in terms of attracting students, I think it's very important to be able to show new generations the impact of the work that we do. I mean, obviously, compensation is very important, as we were all mentioning. Silicon Valley has a lot of opportunities, but the impact that we have on our society, and the impact on climate change, and the impact on so many angles is from where you want to see it. I think it's very important, and I think it's probably one of the main factors why my team has been successful at recruiting really great data scientists, is because we all kind of share that passion, that we really understand and care for the impact that our job has.
Yeah, terrific. I think you four really demonstrated the passion and also the importance working in this industry. Let's keep the lights on and attract more talented students be able to work in the power engineering society. Okay, let's do a rapid fire. Last question. Pathway. The future. If you can identify just one thing and be able to get your organization quickly of any AI application, what is that? Could it be hardware, software, workforce? Just identify one thing. One word.
Data quality.
Good. Marianne?
I would probably say something about implementation, or like process for implementation.
Good. Emma?
Communications. Added a new one, sorry.
Communicate with people, or the communication network?
Communication networks.
Okay, good.
The ability to communicate.
Nicole?
Documentation between our data lakes so we can make a big data ocean.
Great. With that, I would like to thank you all, Nicole, Emma, and Maria, and Marianne, for this excellent presentation and conversation. I would like to hand this back to Hannah.
Great. Thank you guys so much. That was a great panel. We're ending right on time today. So we are going to take another 30-minute break. We will be back at 12 p.m. Eastern for another reverse pitch. Thank you guys very much. We'll see you back here at 12 Eastern.